Hello everyone. All right, this may be it. One of the last video lessons I have for you of the year, pending any extra stuff I want to do. But this is one of the last major topics, and just like volume by rotation, we'll keep practicing it, and then it starts to look the same once you see enough of them. So I'm going to show you what a problem would look like, and then exactly what it means, because they phrase it weirdly, but then I can show you kind of with a simulation like I did the other one, what it's actually asking you to do. So one of the things we can do is we can find the volume of a solid whose base is in the XY plane and whose cross sections, keyword cross sections, perpendicular to the x-axis are squares. Okay, so we're still finding a volume of an object. We're still going to have kind of an area. When we did volume by rotation, we had the area and then we rotated it around the axis, either the horizontal or vertical. This is kind of similar, but it's a little bit more specialized in what you can actually do. Oh, and I forgot to give you so solid whose base is in the XY plane, with base enclosed by, and I have to obviously give you functions, with base enclosed by f of x equals x squared and g of x equals root x. My mistake. Okay, so I have to obviously give you functions, just like I did when we had volume by rotation, volume by cross section, or area. So the way a typical FRQ will look on the AP test, it will give you a shaded area. It'll ask you to find the area, volume using some type of rotation, volume using some type of cross section. So here's the key things to look for. First, it'll say the word cross sections. It will say perpendicular to the x-axis or y-axis. Sometimes it might say parallel. We'll get into all that. And then it will give you some type of shape, typically squares or semicircles or triangles of some type. Those are, and I'll give you kind of the different cases in a little bit. So here's really what we're doing. Let me get this set up. Really what's happening. Come on. Oops. Stop it. Sorry. Should have had this set up. There we go. Okay. My mistake. All right, good enough. So what we're doing is this. We are graphing our two functions. So here is root x, the red one. Here is x squared. They are enclosed between 0, 0, and 1, 1. So between 0, 0, and 1, 1. Let me remind myself how this works. That's right. Okay. The idea is this shaded area, the enclosed area, is going to be laid flat like this. So think about it laying flat, and popping out at you, or popping up in this case, are going to be little shapes. In this case, they're going to be squares, which I'll show you in a second. In other cases, they can be triangles, they can be semicircles. We'll get into all that. But let's see if I click square. I think I can show you one of them. If you look, ready? Lay it flat. You see how that's one square popped up at you? Imagine there's a square at every single cross section of this. So notice also that it's perpendicular. That square is perpendicular to my x-axis. This is the x-axis. That square is sticking up at me perpendicular. And there's a bunch of them. So imagine there's like a ton of them all side by side. Now watch. I'm going to tell it to do like a couple of them. So this is the idea. Imagine that there's an infinite number of these squares sticking up at you to form the like a solid volume, a solid object. And we're going to find the volume of that. So there's with 6 of them. We're going to do it with infinitely many. So this will go up to 100. Here we go. See, these are all the squares popping up at us all along the way to give us this weird slug looking object. And we're going to find the volume of that thing. So we're going to find the volume of this really bizarre object. Again, why are we doing this? It's just another way that we can capture volume of unusual objects. So we're not just limited to cones, spheres, cylinders. Really, any object you dream up, if you can map it using a function, then you can use this method and find the volume that I'm about to show you. And it doesn't work with just squares. So we'll go back. Here we were with a couple squares. Instead of squares, you can do equilateral triangles popped up at you. So a bunch of triangles popped up at you. Kind of looks like a concert hall or something. Is an option. Or we can do even things like semicircles popping up at you. Okay, so the trick is we're going to be able to find the volume of this using a pretty straightforward calculation that's similar to the volume by rotation. Similar. Okay. So I will take you through kind of a step-by-step just like before. All right, so that's the idea. So first thing you should do, step 1, is the same as always. Graph, shade, bounds, f of y's. Find all those things. Find all of those things. Okay. So graph, we already did that a second ago. The graph looks something like, we'll make this R11. So like this and like this. All right. Bounds are x bounds are from where we're starting to where we're stopping. So from 0 to 1. And actually the y bounds in this case are the same. Y bounds are the same. 0 to 1. Okay, so these are the functions in terms of x. Sometimes, just like when we did volume by rotation, you'll need the function in terms of y also. So sometimes you'll actually have to find f of y and use that. So I may as well do it now. So we have y equals x squared square root. So square root of y equals x is one of them. Oops. And then it's going to be similar for the other one. This is a pretty basic example. Square both sides. So basically just flips both of them. Okay, that's all your setup. And then this is the shaded area enclosed by the two graphs. Okay, step 2. Just like in the last time when we did volume by rotation and volume by cross section, you need to figure out which variable are we using, x or y. So here's the key you're looking for. When it said, so x or y. When it says perpendicular to the x-axis, or sometimes it could say parallel to y-axis, those mean the same thing. Perpendicular to the x-axis, which means the cross-section would be this way. That thing in purple I just drew. You're going to use x. But if it says perpendicular to the y-axis, which means parallel to the x-axis, which is not this case, but we'll do one in a second, that's when you're going to use y. So in this case, we are using x's. Okay. Next, begin your setup. So step 3 is going to be your setup. And then also, we're going to find the base length. So our setup is an integral. We're using x's in this case. So this is where I like to do dx, x bounds. And it always works this way, area. we are going to accumulate the area of a bunch of these little things sticking out at us from where we're starting to where we're stopping. Really, that's what the integral symbol does. It's accumulation or adding up a bunch of things together. So this is going to accumulate a bunch of areas to give us a volume. That's what we're going to do. So we set up the equation that we're going to be using. Oh, what's going on? Stop. And now we're going to find what I call the base length. And the base length is just the length of this segment right here. So this is your base length. Well, when we're dealing with x, it's just like we did with area. It's top minus bottom equals the base length. When we're dealing with y, it is right minus left. That would be the base length. So in our problem, we are dealing with x's. So it's the top curve, which is root x, minus the bottom curve, which is x squared. This is my base length. And finally, step 4, final step, use the correct area formula. Now in BC, we derive all these. I show you where they all come from. We may get into that a little bit, but for the sake of time, I'm just going to give them to you. If it's squares, well, if you have a square and this is the base length, so coming back to this picture, that purple thing is the bottom of the square. And remember, the square is sticking up at you. So if we come back to this, we have this is the bottom of a square that is sticking out at us. Well, if this is the base length, which is the top curve minus the bottom, that distance is what I'm calling BL for base length. The area of a square, well, if this is the base length, this also has to be the base length. So the area is the base length squared. So when you're dealing with a square, which I'll show you in a second, all you need to do is plug in the base length and square it. That would go in place of the area. If you're dealing with a semicircle, there's a little bit, semicircle. There's a little more to this one that I'm not going to get into. The formula for this one is pi over 8 base length squared, for reasons I'm not going to cover right now. It's kind of like you're taking the radius, which is half, you're squaring that, which is 4, and then you're taking half of the circle. That's where the 8 comes from. More, I would just kind of have it memorized. And then we have equilateral triangle. The formula for that is root 3 over 4 base length squared. And I think the other one the homework is going to ask you about would be something like an isosceles right triangle. So like this, where this is your base length. Well, if the bottom is your base length and an isosceles right triangle, these two are the same. So the area for this one would be 1/2 base length squared. There are others that we will practice as we go, and I will go through them. I think this is a good start, though. These 4 are good to know. Squares, semicircles, equilateral triangles, or isosceles right triangles. And all you really have to do is, once you know what the shape is, just plug it in. So the last part, I'll kind of come down here so you can see. We had our setup, which was right here. So we'll bring that back. 0 to 1 of our area. Come and look at which one we're doing. We're doing squares in this problem. So it is just your base length, which was what we determined in the last step. Root x minus x squared dx. Done. That would be the volume of this crazy thing that we found. So I won't pull up the calculator today, but we'll definitely start using it soon. Just for the sake of time, we'll go into Desmos and check it. So you would plug this in, make sure you plug it in correctly. Int 0, 1, square root x minus x squared dx. We have this tiny little thing, because remember, it only intersects at 0, 1. It's sticking up at us. The volume of it would be 0.129 units cubed. These are volumes. And that's it. So the keys to remember, and we'll start doing a bunch of practice now, but keys to remember are remember these formulas for area, and it's base length, which is either top minus bottom or right minus left. So it's kind of like area. It's going to feel a lot like area when we're doing these. All right, let's try another one. Same setup. So I'm actually going to do this. I'm going to remove all this. We're going to do the exact same equations, but I'm going to change a few things. Oh, I erased step 0. That's okay. Or I was supposed to. Step 1. I erased my preliminary step. That's okay. Let's do this, though. Let's change this. Instead of perpendicular to the x-axis, let's do perpendicular to the y-axis. Instead of squares, let's do semicircles. Everything else can stay the same. So again, once you get good at this, you don't need to show that you're doing every single step. Typically, the best thing to do is graph it like I did in the last step. Talk about what your curves are. So this curve is y equals x squared, or x equals root y. This curve is y equals root x, or x equals y squared. Bounds, we already remember 0 to 1 for both. Okay, so what's different about this problem? Perpendicular to the y-axis. That means your cross sections are going to go this direction. That's a cross section this time, perpendicular to the y-axis. So that thing in red is going to be your base length, which is going to need to be right curve minus left curve. Right curve minus left curve. And then area, so we can start our setup. The setup is going to be no pi in front on these, remember. There's no pi in front because we're not doing volume by rotation. Where volume by rotation, you have a bunch of like discs. So you can think of it as a bunch of circles being glued together. That's where that pi came from. In these, the area is not circles. It can be squares. I mean, in this case, it's semicircles. But really, only if it deals with circles are you going to see pi. So 0 to 1 area, but in this case, dy. Okay, so the base length is right minus left. The right curve is square root of y. Square root of y. Minus the left curve is y squared. We're doing right minus left because we're working with y. There's your base length. And we just need to find the area. The area, since we're doing semicircles, the formula for that is pi over 8 base length squared. So we have our base length. That just gets plugged straight into the spot for base length. And our volume will be 0 to 1 pi over 8 times root y minus y squared dy. Now, oftentimes you'll see me do this. Since pi over 8 is a coefficient and there's no y in it or variable in it, I can put it out front. Remember, we can move coefficients out front of the integral symbol, just like we did with the pi when we did volume by rotation. And this would give you the volume of this crazy thing that looks like a slug with semicircles. So sticking out of us are semicircles. All right, so let's do another setup, like a completely different setup, but same type of idea. So I'm actually going to clear it out so it's not so slow. All right, one more example, but a couple different ways. Here we go. The base of a solid is enclosed by, where do I have it? Y equals 4, the y-axis, and y equals e to the x. Find the volume by cross sections obtained with, and here we go, two different examples. A, the cross sections will be squares perpendicular to the y-axis. Second one will be equilateral triangles perpendicular to x-axis. Okay, so same setup. So really, once I find it in one, I can find it in both. Let's graph it. So we come here, we come here. Come on. It says y equals 4, which is here. Y-axis, which is here. And e to the x. E to the x goes here and comes up this direction. This is your area. So x bounds. Looks like it's going to be from 0 to this point, wherever they intersect. Well, where do the two intersect? It's where e to the x equals 4. So you can quickly find it by hand, where e to the x equals 4. So in other words, it's just natural log of 4. Natural log both sides. I'm actually going to leave it with natural log of 4. What about your y bounds? Well, the y bounds would be from here, e to the 0, or sorry, it hits the y-axis at 1. When I plug in 0, e to the 0 is 1. So the y bounds are going to be 1 up to where I stopped, which is at 4. So a little bit different for the bounds this time. And it might be helpful to find this curve. If it's e to the x, then in terms of x, it's natural log of y. I just natural log both sides. So that's everything we're going to need to do this problem. So I'll do them kind of side by side. A first says squares, okay, perpendicular to the y-axis, which means this direction. So perpendicular to the y-axis, that means we are using y. So integral y bounds 1 to 4 dy of my area. Well, we are using squares, so the area is just base length squared. What is the base length? It is right minus left. Well, the right curve in terms of y, in terms of y is this one. So the right curve is natural log of y minus, what's the left curve? Well, it's the y-axis, so technically it's x equals 0, so you don't even have to include it, but you could if you want. And that's it, done. Right minus left, kind of like area, but then you're plugging it in, like when you're finding the area between two curves, but then you're plugging it into whatever the formula is for the type of cross section you have. All right, and then let's do B. It says equilateral triangles perpendicular to the x-axis. So now they're going like this that I just drew in purple. So since we are doing perpendicular to the x-axis, we are using x bounds, which would be 0 to natural log of 4. Area dx. But the area, when I'm dealing with equilateral triangles, you don't have to derive this one. You can just trust me that it's root 3 over 4. Base length squared. And what is the base length in this case? Base length in this case, top minus bottom. So a little bit trickier. Top minus bottom. Well, top curve is not really a curve, although we can call it a curve. It's just 4 minus the bottom curve, which is e to the x. Squared, 0, natural log 4, root 3 over 4 in front dx. Done. All right, so not too bad. This is a little bit faster than volume by rotation. And typically these are how they go. So it's not like you have to figure out what big R is and little r is. It's always just right minus left or top minus bottom, depending on the situation. Now, I don't think it comes up in the homework, but just to remind you, sometimes they'll say the cross sections are rectangles popping out at you, or they'll say that this is the base length, and they'll say either the height is 5, or they'll say his height is 5 times the base length. So what would the area be in this case? Well, if this is the base length, the bottom part, and the height is a constant 5, the area would be 5 times the base length. No squared, because it would be 5 times the base length, which is the base. But if they say the height is 5 times the base length, that's the case where this would be 5 times the base length, this distance. So the area in this case would be 5 base length squared, because it's 5 base length times base length. Okay, we will practice these rectangles. I don't think I gave you any on the homework, but that's, once you see it a few times from me, it's essentially all you're ever going to see is these types. I'm almost done, but the last thing is every so often in FRQ, they'll come up with some crazy shape where they'll tell you the area. They'll say the cross section is the shape with area blank, and you just plug that straight in. We'll see one of those soon. I'll find it and we'll do that one in class. But that summarizes kind of volume by cross sections. It's another method for finding volume of abstract objects using this idea of a bunch of shapes glued together, stacking them up to get a weird volume. All right, that's it.